Look across the cosmos, and you'll find one fundamental rule. Nothing moves faster than the speed of light. It is reality's absolute speed limit. But the quantum realm seems to ignore this rule. Under certain conditions, an atom can emit a pair of electrons that fly in opposite directions. One might stay here on Earth, while the other travels to the edge of the galaxy. Because these electrons were born together, they share a connection. If you measure the magnetic orientation, or spin, of the electron here on Earth, you instantly know the spin of its twin, regardless of the distance between them. Information appears to bridge that cosmic gap in zero time. Einstein famously mocked this, calling it spooky action at a distance. To him, it wasn't just strange, it suggested our understanding of physics was incomplete. To fix this paradox, classical physicists offered a common-sense explanation. Imagine I have a pair of gloves, one left, one right. I pack each into its own box and ship them to opposite ends of the world. If you open the box in Tokyo and find a left glove, you know instantly that the box in London holds the right glove. The boxes aren't communicating faster than light. The contents were decided the moment I packed them. For decades, scientists assumed quantum particles worked the same way, carrying hidden variables or pre-programmed instructions stamped into them at the moment they were created. If particles followed a hidden flight plan, then they were independent objects after they separated. The speed of light remained a fundamental limit, and the mechanics of the universe remained predictable. We can test this by measuring the spin of entangled particles at random, mismatched angles, specifically at 0, 120, and 240 degrees. If the particles carry a preset code for each angle, there are only a few possible programs they could follow. If we test these different angles, the math of those fixed programs would force a spin match in at least 50% of our trials. But in the lab, the particles ignore those fixed programs. When the angles shift to 120 degrees, the matches drop to exactly 25%. This result is only possible if the particles are calculating their state at the moment of measurement, not following a code. This statistical discrepancy proves the glove analogy is wrong. Particles do not carry pre-programmed instructions. This realization breaks the concept of local realism, the idea that things have fixed properties even when we aren't looking. Before they are measured, neither particle has a defined state. Erwin Schrödinger showed that they exist in a superposition, a cloud of probabilities where they are effectively in all possible states simultaneously. The act of measuring the first particle forces it to abandon that chaotic superposition and locks it into a definitive physical state. At that exact instant, the probability wave of its twin, no matter how far away it is, recalculates and collapses simultaneously. The observer's measurement of the first particle dictates the physical reality of the second in zero time. The universe is bound by instantaneous connections that defy our classical intuition. This means the universe is not a collection of isolated objects. Instead, it is a vast invisible web where everything that has ever interacted remains fundamentally connected. This quantum ripple means that a change in one tiny state instantly redefines its entangled partners throughout space. However, we cannot use this web to send a message faster than light. Because the outcome of any quantum measurement is inherently random, you cannot force the first electron to pick a specific spin to encode a text. This physical law provides an instant correlation of reality, but because we cannot control the outcome, it cannot function as a controllable telephone. While we cannot send faster-than-light messages, we are now using this wave function collapse for a highly practical technology, quantum cryptography. Data is encoded onto entangled photons and sent through fiber optic cables, like the glass strands shown here. If a hacker attempts to intercept or measure a photon midstream, the wave function instantly collapses, scrambling the data. This physical law makes undetected hacking impossible. By manipulating these invisible threads, humanity is building a level of security that was previously impossible.